All right, enter the gamma distribution. You might have heard of gamma rays from the Incredible Hulk. It's a little bit different from what we're going to be doing here. Gamma distribution, tricky distribution, but actually has a pretty nice story, unlike the beta, which we're kind of learning about simultaneously, that we can wrap our head around. So the gamma distribution, if we know the exponential distribution, which we know is sort of the waiting time until like a bus arrives, and we know it has this really nice memoryless property. The gamma distribution is the sum of IID exponentials. So think about it. Let's unpack that for a second. We need to have exponentials that are identical, so they have the same rate parameter. So lambda. We can't add an exponential 4 and an exponential 5. It's got to be like a bunch of exponential 1 random variables, and they also have to be independent. And that gives us a gamma. So here, similar setup as to all the other random variable shinies. My two parameters, alpha and lambda. Alpha dictates the number of IID exponentials that I add up. Lambda dictates the rate parameter of each exponential. Number of draws, as usual, tells us how many points to plot. And we're going to start, as usual, with 1,000. So first, let's set alpha equal to 1. This is just an exponential, right? Just like how the negative binomial, if we set r equal to 1, where r is the number of the number of successes that we're waiting for, we know that's just a geometric. And similar to binomial, when we have n equals 1, it's just a Bernoulli. When we have gamma 1 comma something, it's just an exponential with that something as the rate parameter. So here this should look like an exponential, and it does. As we start to increase alpha, right, this is adding the number of exponentials that we're waiting for. So notice we'll start at 1, and this kind of goes from 0 to 3.5, or like it's really clumped. Most of it's below 1, right? But as we increase alpha, we start to see it, creep to the right a little bit, which makes sense because we're adding waiting times. Even though each waiting time is probably less than one on average, we're adding a bunch of them. So overall, we get greater than on average greater than 1. So that's the alpha parameter. Lambda, just like an exponential, if we decrease lambda, we get larger values of x, of the random variable. So if we decrease lambda to 0.1, whoa, all of a sudden we jumped up to 50. Whereas if lambda goes up to 10, we're going to have, values that are well less than 1 usually. The reason being is because, recall, the expectation of an exponential is 1 over lambda. So the larger lambda is, the less time we expect to wait, the less on average. And as usual, you can hit go a bunch of times to see different samples, and you can decrease the number of draws to see sampling variability in small sample cases.